When you want to keep food fresh today, you simply open a door and place it in a chilled, sterile box. But if you walk onto a factory floor in 1875, you find a deafening corrugated iron building filled with the stench of molten metal, the hiss of steam, and hundreds of people scrambling to seal food inside metal cylinders before it rots. For most of humanity's history, surviving the winter meant defeating the harvest cycle. Expanding nations and marching armies required massive amounts of calories, but their supply chains were fragile. Without a reliable way to keep food edible for months at a time, military campaigns and westward expansions routinely collapsed from scurvy and starvation. Look at the crude construction of these early 19th century containers. Invented in 1810, the first tin cans were actually thick wrought iron vessels coated in tin. They were incredibly heavy, sometimes weighing more than the food inside them, and engineered almost exclusively for institutional and military use. Because they were built like iron vaults, the manufacturer's opening instruction was to use a hammer and chisel. The tin can was invented in 1810, but the first practical can opener was not patented until 1858. For nearly half a century, hungry soldiers in the field had to improvise, literally smashing their meals open with heavy rocks and rifle bayonets. During the American Civil War, the Union Army needed rations that could survive rail transport and months in the field. To meet this demand, the federal government poured money into northern factories. In just 4 years, production leaped from roughly 5 million cans a year to 30 million. Millions of soldiers learned to eat corn, beans, and beef out of metal containers. When they went home, they took that expectation with them. Military necessity turned a slow, handmade craft into an unregulated mass-market industry overnight. Inside these booming early factories, a specialized group of craftsmen known as boss canners held absolute control. They shaped the containers by hand, cutting flat sheets of tin plate and curving them over cylindrical forms. Cannery owners were entirely dependent on these men, who fiercely guarded their techniques and dictated the pace of the entire facility. This diagram illustrates the dominant container of the mid-19th century, the 4-piece hull and cap can. Workers joined the body, top and bottom, by melting a 50% lead, 50% tin solder directly onto the seams. Once the factory filled the can through the hole in the top, a final cap was soldered directly over the food. Under brutal piece rate payment systems, speed was everything. The fastest workers, often inhaling toxic acid flux fumes and enduring the intense radiant heat of the soldering irons, sealed the caps of up to 1,500 cans in a single day. Notice what happens as highly acidic foods like tomatoes or peaches fill the interior. The acid actively leaches the heavy metal from the exposed interior solder joints directly into the food. Lead is a cumulative neurotoxin, meaning small repeated exposures cause permanent neurological damage over time. The industry was solving a caloric crisis while simultaneously delivering nerve damage to the public. In an era before modern industrial hygiene or toxicological testing, this fatal trade-off went largely unnoticed. Even with frantic hand soldering, the industry faced a massive thermal bottleneck. Submerging sealed cans in standard boiling water at 212 degrees Fahrenheit took up to 6 hours to destroy spoilage bacteria. During those hours, vegetables turned to mush, meat fell apart, and factory floors stalled while waiting for batches to finish. In 1874, a Baltimore manager named A.K. Shriver patented a commercial steam pressure retort. A retort is essentially a massive industrial pressure cooker. By injecting superheated steam into a sealed vessel, Shriver pushed processing temperatures to 240 degrees Fahrenheit, cutting the required sterilization time from 6 hours down to just minutes. Facilities scaled up immediately. A single retort room might contain a dozen massive cylinders processing thousands of cans at once. This required relentless physical labor as crews continuously loaded and unloaded heavy crates of superheated metal using hand trucks. Look closely at the faces in this cannery photograph. The incredible output of these new machines was powered by immigrant families and young children. Kids as young as 7 or 8 sat on crates, shucking oysters or stringing beans for piece rate wages, sometimes falling asleep at their stations amidst the deafening noise and open machinery. The steam retort solved the speed problem, but early canners still did not fully grasp the biology of why food spoiled. Relying on exhausted children and unverified temperature schedules meant the industry was scaling up the production of potentially dangerous food. While vegetable canneries dominated the East Coast, the Pacific Northwest and Alaska presented a different challenge. Salmon canneries operated as remote, self-contained industrial communities, requiring a massive scale of rapid processing to handle millions of fish during the short spawning season. Panning across this historical photograph, you see the highly skilled workforce that built the Pacific salmon industry. Chinese immigrant laborers organized through a labor contractor system performed the exhausting work of rapidly butchering the raw fish. A skilled seaman butcher could clean and prepare about 2 salmon per minute. In 1903, a Seattle inventor named Edmund A. Smith developed an automated machine that could slit, clean, and extract the viscera of the salmon in a continuous mechanical loop. It processed 110 fish per minute, effectively replacing the work of up to 50 human butchers. The inventor and the cannery owners explicitly named this machine the Iron Chink. They used the racial slur openly in patents, trade publications, and public demonstrations to proudly advertise exactly what the machine was designed to do: eliminate Chinese labor from the factory floor. The rapid adoption of this butchering machine reveals a dark reality of early industrial expansion. Cannery owners utilized technology to mass-produce food and aggressively erase a minority workforce they depended on but deeply resented. The ultimate reckoning for canning food without understanding microbiology came from Clostridium botulinum. It is an anaerobic bacterium, which means it thrives perfectly in the oxygen-free environment inside a sealed tin can. It produces a lethal neurotoxin that is completely invisible, leaves no odor, and doesn't change the taste of the food. In late 1919, disaster struck. Commercially canned black olives packed in California carried the toxin to dinner tables across the country. At least 18 people died. The press coverage devastated the nascent industry, proving that an invisible mistake on a factory floor could kill a family thousands of miles away. In this photograph of the Pure Food Laboratory, you can see the industry's survival pivot. Facing total collapse, canners funded scientific commissions to study bacteriology. Researchers finally established precise, legally mandated temperature and pressure schedules based on the specific acidity of different foods, replacing dangerous intuition with strict laboratory science. Around this same time, the industry finally eliminated the threat of lead poisoning. An inventor named Max Ams developed a mechanical process called the double crimping method, creating what became known universally as the sanitary can. This animation details the double seam method. Rollers press the edge of the can lid and the can body together into 5 interlocking layers of metal. A thin strip of rubber compound flows into the microscopic gaps, creating a perfect hermetic seal. No heat is required, and not a single drop of toxic solder touches the container. Today, you can easily pull a perfectly safe can of tomatoes from your pantry without a second thought. But that effortless convenience is the direct result of a brutal trial and error history, bought and paid for with a century of lost fingers, exhausted child labor, toxic metal exposure, and the eventual triumph of strict laboratory science.